Absolutely, yeah. So, without any further ado, I'm going to welcome Professor Sean Freeman from the University of Manchester to introduce us.
Okay, so thank you, Peter. So, welcome everybody to Manchester, welcome to the university, and welcome to the physics department. Well, at least the old premises that we vacated in the early 1960s. It's my job to welcome you, which I've just done, but I'm going to say a few remarks to set the scene. So we're here today to mark 100 years since the publication of a series of 4 papers by Ernest Rutherford, the then Langworthy Chair of Physics at the Victoria University of Manchester. We've got a very interesting programme of expert speakers. I'm not an expert on the historical subject matter of today, but as a way of introduction, I wanted to set the scene and also make a few comments as a current jobbing nuclear physicist. Rutherford moved to Manchester in 1907 after performing work on radioactivity at McGill in Canada that won him the Nobel Prize for Chemistry. It probably attests to Rutherford's genius that arguably his most famous work was done after the Nobel Prize and done here in Manchester. So between 1907 and the start of the First World War, he achieved a number of important results that defined the start of the field of nuclear physics. He sorted out the structure of the atom, he discovered the atomic nucleus with his interpretation of the famous Geiger and Marston gold foil scattering experiments. Now that finding, along with football, cotton mills and Boddington's beer, is still used in marketing the city of Manchester today. I should add other Manchester beers are available. It proved that alpha radiation is composed of helium nuclei, and with Geiger developed the first ionisation chambers to measure radiation. But the work we discussed today is essentially the first initiation and observation of a nuclear reaction. The work was done during World War I under rather difficult conditions. Rutherford did what he could in between war work. It followed on from some initial measurements made by Marston, as from the gold foil experiment, who found the intriguing result that swift hydrogen nuclei were observed when investigating the passage of alpha particles through gases. Rutherford's work proved categorically that these particles were indeed protons, and found that their incidence dramatically increased with the introduction of nitrogen gas into the apparatus. Many more than could be explained by protons being knocked on from any hydrogen-containing material in the apparatus. But he very carefully and painstakingly eliminated all the possibilities, other than it was the alpha particles interacting with nitrogen nuclei that produced protons via a nuclear reaction. Now, later experiments showed that what was true with nitrogen was also true for other gases and metal foils. So he saw protons liberated from nuclear reactions on many different targets. This was really the discovery that protons were a universal constituent of all atomic nuclei, fundamental constituent of atoms. Rutherford remained actually a little bit bothered. He couldn't quite relieve himself of a paranoid anxiety that the apparatus wasn't completely free of hydrogen and the protons were just being knocked forward from some unrevealed hydrogenous material. But in 1921, he did careful experiments with James Chadwick in Cambridge that showed that the protons knocked on from hydrogen gas were demonstrably less energetic than those liberated from reactions on nitrogen. And later, painstaking research done by Patrick Blackett at Rutherford's suggestion, again in Cambridge and published in 1924, successfully used a cloud chamber to find visible tracks of the disintegration that Rutherford had discovered in Manchester. And in a sense, Blackett became the first person to reveal the details of the process, an alpha particle fusing with a nitrogen nucleus to form an excited fluorine system, which then ejects a proton, leaving a residual nucleus of oxygen. Now, my esteemed colleagues will give you a much more detailed account of the context, the experiments, and the implications, and I hope that they all forgive me for any historical inaccuracies in the account I've given so far. I'm not a historian, I'm an experimental nuclear physicist, but I'm not running the School of Physics and Astronomy in Manchester. But perhaps I could sketch out some of the implications of this results in terms of scientific and societal impact, and how its echoes still influence us today. In my own field of curiosity-driven nuclear physics, we're still performing nuclear reactions. We use them to measure the shapes and sizes of atomic nuclei and to probe the quantum motion of protons and neutrons inside the nucleus. Now, for many years, the ingredients we use in these reactions has been rather restricted just to those nuclei isotopes that we can find naturally occurring, so stable or very long-lived things. And that correspondingly means that we can only make a small subset of the isotopes that are expected to exist. Indeed, we were missing out on many of the isotopes that only exist for fractions of a second, but fleetingly play very important roles in huge chains of nuclear reactions that occur naturally in extreme astrophysical science. And it's those processes that manufacture the full range of chemical elements that we see around us in nature, out of the hydrogen and the helium that was produced in the Big Bang. However, modern nuclear physics, there are a number of new facilities being built around the globe that use a primary nuclear reaction to create a radioactive nucleus, which is then itself used to initiate a second nuclear reaction. For these radioactive nuclear beam facilities, we're studying strange and exotic nuclear structure and understanding the nuclear synthesis that happens in the universe. My own research team recently commissioned a spectrometer at CERN to measure some of these nuclear reactions induced by radioactive nuclear beams. Indeed, Rutherford's own nuclear reaction, alpha particle in and a proton pops out, so-called alpha P reactions, turn out to be very important processes that happen in heavy stars and in accretion disks of certain binary systems. This is a reaction that, after Rutherford performed it, drove several different research avenues in nuclear physics in the first part of the 20th century. During the 1920s, it became clear that alpha particles from radioactive sources was a rather restricted approach to performing nuclear reactions. In order to initiate a nuclear reaction, you have to push two nuclei together within the restricted range of the nuclear forces. Indeed, Rutherford's reaction was the first indication that nuclear forces exist. And you need energy to push those two things together, and the energy coming from particles from radioactive sources is rather limited. So that drove an international competition in the 1930s to build the first particle accelerator. It was narrowly won by Cockcroft and Walton in Rutherford's own laboratory in Cambridge, and the development of accelerators with higher and higher energies in subsequent decades, supported by some early cosmic ray observations, actually gave birth to the field of elementary particle physics, which is now performed using some of the highest energy accelerators available, such as those at the IHC at CERN. The accelerators have also found practical uses for society, from cancer therapy through to production of medical isotopes. They're used as sources of light and X-rays, used to probe the structure of materials, and also used in security scanning. Rutherford's work provoked a number of other research groups in the 1920s to survey reactions of alpha particles on various targets. Groups in Paris, Berlin, and Cambridge found some unusual and exciting results in the bombardment of beryllium targets, which led to the discovery of the neutron by Chadwick in the mid-30s. And ongoing research into neutron-induced nuclear reactions led to the discovery of fission, the development of nuclear reactors, and other, perhaps less positive, fusion and fission devices which were used as weaponry. So the impact of these results, obtained in rather rudimentary labs in a northern industrial city, but by a genius with careful and painstaking approaches, have resonated down the decades, initiating whole new fields of physics, supporting other areas of science and engineering, as well as helping to shape the society we live in today. So we have an exciting programme to listen to today. It will be interesting to hear the details, the context, and the implications of those 4 papers which were published in the summer of 1919 from a series of experts in the scientific history and historical context. Before we start, though, I would like to sincerely thank the organisers, Neil Todd and Peter Owens for all their efforts in making the event happen today, to the speakers from whom we're just about to hear, and also to everybody here today for your participation in the event. Let's get on with the day.